Hi guys, this is Mrs. Allison, and today we are going to finish up our 9-5 with a venture into vectors. Now, I would like you to start with a warm-up, so hit pause, try this warm-up, and then come back. Okay, so the graph of the polar curve r equals 2 minus 4 sine theta is shown, and we want r, the shaded region, and what we want to do is we want to be able to find the area of that shaded region. So if we look at the points that were given, this 0 and this theta, sorry, that doesn't say theta, pi over 2, and I were to plug in 0 into this equation for theta, I would have 2 minus 4 sine of 0, and the sine of 0 is 0, so I would just get 2. So the first point that I have is the point 2, 0. That would be this point right here. Let's make that pen tip just a little bit skinnier. And if I were to plug in pi over 2, when I plug in pi over 2 to that same equation, the sine of pi over 2 is 1. So I get 2 minus 4 times 1, so I get negative 2. So I have the point negative 2 pi over 2. Well, that's actually this point right here. Negative 2 pi over 2. And so I need to figure out what this point is right here, because in order to find the area, remember that the area that we have is going to be the 1/2, oops, let's do that in a different color, 1/2 the integral from the lower bound, which is 0, to the upper bound, I don't know that one, I don't know what this point is, times 2 minus 4 sine theta squared d theta. So I need to figure out that upper bound. And the way I'm going to go about doing that is I'm going to set 0 equal to, because that's what the value is right there, 0 equal to 2 minus 4 sine theta. And I'm going to solve. And solving this, I get that 1/2 equals the sine of theta. And where sine of theta is 1/2 is when theta is pi over 6 or 7 pi over 6, but that doesn't fall in our bounds. So pi over 6 is that upper bound that I'm going to use. All right, and then this becomes a calculator question. And when I type this in my calculator, I'm going to type it just as it's written. I get 0.3377. Since a lot of you are in physics, please make sure your calculator is in radian mode. Physics uses degrees. We use radians. So make sure you get that switched. All right. Now, to find the equation of the line tangent to the graph means I need a slope. But the problem is, if I need a slope, I need to figure out dx d theta and dy d theta so I can figure out a dy dx. And I don't have that information. So I'm going to need to parameterize my equation. So if we know x equals r cosine of theta, I know what r is. I know r is this 2 minus 4 sine theta, so in place of r, I'm going to put the 2 minus 4 sine theta. So x equals 2 minus 4 sine theta times the cosine of theta. And then I'm going to take the derivative. And this derivative is going to require a product rule. So we would get negative 4 cosine theta times cosine theta plus 2 minus 4 sine theta, I'm not writing the plus and you'll see why, times the derivative of cosine, which is negative sine. So this will change to a negative sine of theta. And I'm going to evaluate that when theta equals 0. So when theta equals 0 there, I get, I get negative 4. Now I'm going to repeat that process with the y. So y equals r, sine theta. So y equals, and again, I'm going to substitute in place for r what r is. So I get 2 minus 4 sine theta times the sine of theta. I could distribute that sine of theta in. I'm still going to get just as big of a mess. So I may as well just use the product rule like I did before. So we get dy d theta equals negative 4 cosine theta sine theta plus, this one will stay plus, 2 minus 4 sine theta cos theta is the derivative of sine. And I'm going to evaluate that when theta equals 0. And when I do that, I get 2. So I know then that my slope, which is dy d theta over dx d theta, which when reduced gives me dy dx, equals negative 2 over 4, or negative 1/2. So my slope's negative 1/2. Well, now I need to find the point. And the way I'm going to find the point on these problems, is I'm going to substitute in x of 0 for theta, and my theta, or my x equation, was 2 minus 4 sine of theta, so 4 sine of 0, times the cosine of theta, cosine of 0. And we get x to be, well, this would be 2 minus 0 times 1 equals 2. And then I'm going to repeat the process with the y. So 2 minus 4 sine of 0, and I would get 2 minus 0 times 0, which is just 0. So the ordered pair that I have, my slope is negative 1/2. My point we just found to be 2, 0. And now I can write my equation. Y minus 0, although that seems silly to write, equals negative 1/2 x minus 2. And there's my equation that would be tangent to that curve at theta equals 0. All right. Now what we're going to do is we are going to focus on vectors. Now, you had a whole unit on vectors last year in trig pre-calc, and it would have come in first semester. So it's been a little bit of time. So I am going to go through all of the content, but those of you that feel pretty strongly on your vector work, feel free to skip this first part until we get to the derivative work. Or if you want a refresher, put me on 2-speed and just see if you can cruise through this and feel good with the information. So, vectors. What do we know about vectors? Well, we know that they're a quantity that has direction and magnitude. Now, their notation. Their notation can be notated several different ways. First, you may see a vector notated with a bold, that's really bold, a bold letter. Typically V, U, W, those are our vectors. I'm not sure why. V makes sense, vector. Or you could see the vector notation with a V with this arrow up top, like a half arrow up top. And you may see the notation with the V and a hat. We'll call it a hat. I don't know what the real name for it is. Hat sounds good enough. Oftentimes in physics, they use the hat. In fact, if you watch some physics videos, they say V hat to imply that it's a vector. The bold, you'll see that typed a lot. It's really hard to write a bold V. So I would say the most common notation for vectors is going to be this one with the arrow. And that's probably the one I'll use the most. Now, if we're given a picture of a vector, so I have an example of a vector here that we're going to use a couple times, and you can see that its end point is 4, 2. This vector is notated with these angled brackets as 4, 2. Now, you could also see this vector written without the angled brackets, but it would need to have the vector notation, and you may see it in parentheses, but it's easy to get parentheses confused with an ordered pair, and 4, 2 is not an ordered pair, although that is where it is on the Cartesian plane. It's not an ordered pair. It's not a single solitary point. It's a vector that moves in that direction, and its ending point, its terminal side, is at 4, 2. These are typically called component form. Now, you may also see this vector written in matrix notation. Well, this is a vector notation where we have a vertical, what looks like a matrix, and you can see it in that way. I cannot remember the name of that. But the other most common one that you're going to see would be when we have a 4i plus 2j. This is This stems from our unit vectors. Our unit vectors look like this. Let's do it in a different color so you know I'm talking about something different. Our unit vectors look like this. If we have a grid or a coordinate system, and I have a vector that goes up like this, this vector right here is what we call the J vector, and it's usually with a hat, and it is the vector 0, 1. It's a unit vector, 1 unit in length. The I vector is in the x direction, and the I vector, which we would write I hat, is the vector 1, 0. So those are unit vectors. So if we say 4i hat plus 2j hat, it's because we did 4 times the vector of 1, 0, plus 2 times the vector of 0, 1. And that's where we get the vector for 2. So unit vectors and component form. Those are going to be our most common that we'll use. When you get into Calc 3, we focus a little bit more on this matrix notation right here. Okay, let's move on. Magnitude. The magnitude is the length of a vector. And the way we find the magnitude, or the way we notate the magnitude, can be done one of two ways. You may see these single bars. You could also see double bars. You could see it written either way. They are used interchangeably for magnitude. And it just kind of depends on where you see it or what mood somebody's in, maybe even. And the way we find the magnitude is the magnitude will be the square root of each of the components of the vector. So in our vector v, our component 1 squared plus component 2 squared, and the square root of that will be our magnitude. Now, if we look at the problem that was up above, the one we looked at before, we might say that the magnitude of v is equal to 4 squared plus 2 squared, so the magnitude of v would be root 20. I probably would simplify it to root 5, but the magnitude, the length of the vector, is how long the vector is. And if we want to think about it in terms of Pythagorean theorem, it's a squared plus b squared equals c squared. We've solved that. That's the length of that vector. Now, the direction of the vector, which way the vector is moving. The direction of the vector is based off of trig ratios. And the trig ratios that we're going to use are going to be tangent. And so this angle that is here will be our theta. And so when we talk about the direction is theta equals the tangent inverse of y over x. The y component or the j component over the I component. So in our example up above, I would say that our direction is theta equals the tangent inverse of 2 over 4. So theta equals the tangent inverse of 2 over 4. And yeah, I could plug that in my calculator, but I'm guessing that part you can do. All right, a unit vector. A unit vector is a vector whose magnitude is length, equals 1. So a unit vector is a vector whose magnitude or length is 1. And the way that we find the unit vector is we take the vector itself and divide by the magnitude of the vector. Okay, so we take the vector itself and divide by the magnitude of the vector. You will notice that the result of the unit vector is another vector, whereas the result of the magnitude is a scalar, meaning it is just a single quantity, it is not a vector. Let's look at it in terms of that example up above. My unit vector for this one would be the vector 4, 2. We said that was the vector 4, 2. And the magnitude being root 20, means my unit vector would be 4 divided by root 20 and 2 divided by root 20. And that would be my unit vector. If I calculated the magnitude of that, the magnitude of this vector right here would be 1. And you could check that if you wanted. Okay, moving on. Adding and subtracting. I told you, crash course. Now let's look at adding and subtracting. And to do this, let's just briefly talk about how. When we're adding or subtracting, we are literally just going to add or subtract the components in the same position. So we're just adding or subtracting components. Now, I don't have another vector up top, so let's just give a vector. Let's give 2 vectors. So u is going to be the vector 5, -3. And then v will be the vector I hat plus 4j hat. If we want to add these 2 vectors together, u added to vector v, we will simply add their components, their like components. So 5 will add with the component of the I, so 5 plus 1. And then the second component, -3, will add to the j component, so -3 plus 4. And so we get 6, 1 for the vector. And when we add or subtract, we get vectors. Now, if we multiply, really the only multiplication we can do is scalar multiplication. And to do that, we simply multiply the scalar by each component. And so if we use that same u and v that we just did, so the u is the vector 5, 3, and v is the vector I hat plus 4j hat. If I want to do 3 times the vector u minus 2 times the vector v, we will get 3 times 5, 3, the vector, minus 2 times 1, 4. And I would simplify the components and probably would do this in one step, but we're going to take 2. So we would get 15, 9 is the vector 3u. And then I'm just going to change the sign, but put that as positive. So this would give me -2, -8. So now I'm adding the 2 vectors. Adding these 2 vectors, we get 13, -17. Oops, this should have been a -9. Nope, I put +3, so we're just going to leave it. And that won't be 17, that will be +1. I intended to keep those vectors the same, but they are different. So there we go. That should be a review in a nutshell of everything you've done with vectors so far. And now moving forward, we'll move into the calculus of our vectors. So let's move on. We are going to talk about vector-valued functions. So a vector-valued function is usually notated as r of t, and it equals some f of t times I plus g of t times j, or f of t I hat plus g of t j hat. And what it does is it takes the variable t that we substitute in and returns a vector. Now the domain of the vector-valued function is all of the t values for which both component functions are defined. So as long as it's defined on f of t and g of t, those values will be in my domain. And what you should notice is that each of these can be written as parametric equations. Oh darn, I didn't want this x to split the line. But the parametric equations x equals f of t and y equals g of t. So vector-valued functions are just the sum, using vector notation, of parametric equations. Now, we can also represent rectangular equations using vector-valued functions. They're not really the same, but the positions they describe in space are the same. So the end result, the path that we trace, ends up being that same path. Okay, so let's look at how we can sketch a vector-valued function. The first thing is we should notice that the vector, we could rewrite it. This vector r of t could be rewritten as 4 cos of t, 2 sine t in this component form. Now, the parametric equations that go with it, if we were to look at those, and it's easy to do right here, the parametric equations that go with it would be x equals 4 cos of t and y equals 2 sine of t. And those are our parametric equations. Now, we could eliminate the parameter, messy here, but we could do it, and rewrite this in rectangular form, although that's not the exercise we're going to do today. I just want to look at how we sketch this graph. Okay, so if we start substituting in values for t, and it says that t is between 0 and 2 pi, and with trig, I know that the quadrantal angles work the best. If I substitute in 0, I would get 4 times the cosine of 0, comma 2 times the sine of 0, which means I get the vector 4, 0. Now the vector 4, 0 actually represents, if we start in our initial side of 0, 0, represents a vector that's direction is right here. So the position of the vector ends right here at 4, 0. Now if I keep going and I look at some of my other angles, and I'm going to take a shortcut. If we plug in pi over 2, the cosine of pi over 2 is 0, so the first would be 0, and then the second would be 2. And so I have this vector right here. Now, we could keep going all the way around our quadrants, and what we would see is this gives us negative 4, 0. We have a point here. We get 3 pi over 2. We get 0. 3 pi over 2. We get 0, negative 2 right here, and that is pointing right there. And what happens is, as these vectors move around the circle, maybe we even look at, say pi over 6. And if we take 4 times the cosine of pi over 6, we would get 4 times root 3 over 2, which would give us 2 root 3 comma 1, because the other one was 1/2. And so we get this point right here where we have a vector coming here, and you can see this rotation that is happening. Oops, we'll pretend that hit. Darn. Didn't hit it again. We can see this rotation that's happening, and we have directions going around this vector valued function. Now, if we were to sketch the same parametric equation, where x is 4 cosine of t and y is 2 sine of t, we'd get the same points around that equation with that same direction. And so you can see this vector valued function take shape. Now, let's talk about the calculus of the vector valued function. The first thing that we want to deal with are derivatives. And when we notate derivatives, it's not going to be notated any different. We're going to say the derivative with respect to t of some r of t, or we may say the derivative with respect to t of the vector x of t comma y of t. But the end result is, when we take the derivative of each of these, we're going to take the derivative of each component with respect to t. So the derivative of that vector valued function is the derivative of each of the components. So for example, if I have this r of t equals ti plus t squared j, maybe I rewrite this in component form. This gives me t squared. If I want to take the derivative of this, if I take it in its unit vector form, I would have 1i, I'm going to use the hat, it's hard to make the bold, plus 2tj hat, or in component form, the derivative would be 2t. Okay, let's take the second derivative. Second derivative in component form would just be 2j, because the I hat would go away. It's just a constant in front of it. The derivative of that constant would be 0. Or if we look at it in component form, the derivative of 1 is 0, and the derivative of 2t is 2. Okay, when have you seen a first and second derivative? hopefully your first thought is position, velocity, and acceleration. That's because vectors are position, velocity, and acceleration. The definition of a vector is that it has magnitude and direction. It's pointing to some point in space that is a position of a curve. It's a parametric equation that is the position when t equals some value of our x and our y. Okay, so that's derivatives. Now, we need to take integrals of vector-valued functions. And guess what? When we take the integral of vector-valued functions, it's too going to be a vector, and we can integrate each component separately. So the integral of our vector-valued function r of t is the vector of the integral of x of t and the integral of y of t with respect to t. Oops, don't need that. I need an angled bracket. And that's how we find the integral. Now let's look at an example of finding the integral. When we find this integral, what we're going to be doing is we're going to be taking the integral of each component. And sometimes it's easier just to see in component form. And when we do that, the integral of t squared would be t cubed over 3. But I need a plus c, because when I do an indefinite integral, we need that constant of integration for each component. So I take the integral of 1 over t, I'm going to get the natural log of the absolute value of t, but I also need a constant of integration there. So you need a plus c for each component. Now, this could be written a little bit differently. Sometimes it may be easier to rewrite this vector as t cubed over 3 plus, t cubed over 3, comma, the natural log of the absolute value of t plus some constant vector, okay? So we can write it as a constant vector where I'm simply just taking these c1, c2 and putting them as components of their own vector. Maybe it looks like the form we have here, where we have this constant vector. You may even see it written this way, where we have t cubed over 3, comma, the natural log of the absolute value of t, that vector, plus some vector c1, comma, c2. And we know that would take me back to the same thing because in vector addition, we add the components together. Okay, so let's look at the main application where we're going to see vectors used in calculus. You knew we were going to talk about position, velocity, and acceleration. So let's come up with some formal definitions for the vectors of position, velocity, and acceleration. For position, the position vector is usually notated with an s, the s vector. You may sometimes see it as an x vector, which can get a little bit confusing when you have components of x and y, but sometimes you may see this vector written as an x vector, like this. Okay, but most of the time, my position vector is going to be s. I can't say most of the time. Should be written as s. And it's just the components of x of t and y of t. And then what do we know about velocity? Well, we know velocity is the derivative of the position. So my velocity vector is going to be the derivative of each of these with respect to t. And maybe we even write it that v of t is the derivative of s of t is that vector. Now, why is that? Well, we know that velocity has direction because it is a vector that is made up of the dx dt, the change in x with respect to time, and the change in y with respect to time. And it's this vector that points right there. So the velocity vector has direction. Now that's going to look a little bit different when we talk about speed, so hang tight to that. Acceleration. What do we know? Well, we know acceleration is really the first derivative of the velocity, which is the second derivative of the position. So we have the second derivative of the position here, the vector. That's acceleration. Now let's talk about speed. Speed is what we call a scalar. It is not a vector. Speed is just a quantity. It does not have direction. It does not have magnitude. It is just magnitude. It does not have direction. So speed is a scalar. And when we notate this, you are going to see it as the magnitude of the velocity. Remember, magnitude could have 2 bars or 1 bar. The magnitude of velocity. And it equals the square root of dx dt squared plus dy dt squared. Why? Because the speed is the length of this vector. So the speed is the length of the velocity vector, not the position of the velocity vector like velocity is. So speed is the length, the magnitude, hence the magnitude. So let's look at an example. This would be an example of a no calculator. A particle moves in the xy plane so that at any time t is greater than or equal to 0. The position of the particle is given by x of t equals t cubed plus 4t squared, and y of t equals t to the 4th minus t cubed. And then it asks me to find the velocity. So make sure you know what you're finding. We are finding the velocity at t equals 1. So we know the velocity is really the derivative of the position. And we know the position was given by this x of t, y of t. Now maybe you want to look at it in vector notation, and that would be fine, or in the component form. And this would be your position vector. So when we go to talk about our velocity vector, I'm just going to take the derivative of each of those positions. So we'd get 3t squared plus 8t, comma, 4t cubed minus 3t squared. So this would be the velocity vector. Now it asks for the velocity at 1, so I'm just going to substitute in 1 for t. Doing that, I get 11,1. All right, see if you can find both the speed and the acceleration vector at t equals 1. All right, speed. Speed, we know, is the magnitude of the velocity vector. So speed is the square root of the velocity vector squared. So 11 squared plus 1 squared. Now I could find a general form for the speed, but this one asked for it specifically at t equals 1. And so I would have the square root of 122. Notice speed is a scalar. It's a one quantity. It's not a vector. All right, the acceleration. Acceleration is the derivative of the velocity, or the second derivative of the position. And so we get 6t plus 8 and 12t squared minus 6t. Now it did ask us to evaluate it at t equals 1, so the acceleration at 1 is 14.6, the vector 14.6. How'd we do? All right. One of the things that's common for AP to do is to give you only the velocity vector and then ask you to work your way around the problems. We've seen this before when they weren't dealing with vectors. They were just dealing with functions of x. So first thing we want to remember, and you'll want your calculator. So if you don't have it, hit pause and go grab it, because this is a calculator question. First thing we want to remember is that the velocity vector is really the derivative of the position vector. Okay, So when we talk about displacement, displacement is expressed in an interval. Like how far is this particle displaced at? Find the displacement of the object at. And it will give you a range of values. And the way that we do that is we take the integral from a to b of my velocity vector, which means that my vector, and this ends up being a vector as well, is the integral from a to b of each component of my vector. So dx dt, and the integral from a to b of dy dt. So that's the displacement. Now, the distance traveled. Is that going to be a vector or is that going to be a scalar? Well, it's going to be a scalar because when we talk about distance traveled, we give an exact value or an approximation, but we give a value. We don't have a vector, we have a value. So this too is a scalar. And we talked about speed was a scalar, so is distance traveled. Now, distance traveled is going to be, the way I find it is I take the integral, the sum of, from a to b, of all of the magnitudes of v. Okay, let's rewrite that. I have the integral from a to b, and we said the magnitude of v is the square root of dx dt squared plus dy dt squared dt. Does that look familiar? It should. This right here, that is the arc length. We've already done that. Arc length equals the distance traveled. So we've done the distance traveled. Even with the velocity vector, it's the arc length. All right, let's look at position. Well, what is position? We know it's the first derivative. So I know we need to take the antiderivative of my velocity vector. But we're going to use the idea of the fundamental theorem of calculus. And just to the side, I'm going to write over here, remind ourselves about the fundamental theorem of calculus. Do you remember the fundamental theorem of calculus said that from a to b of some function, we would get s of b minus s of a using the vector notation? Do you remember the fundamental theorem of calculus that said that? Do you remember when we talked about the accumulation in integrals? Same idea. If I want to find some position, I'm going to take my initial position at A, add to it the integral from a to b of the v of t dt, the position, or the velocity vector, and it's going to equal the position at B. Okay, let's review. This is my initial position. This is my displacement. And this is my final position. So we can see that the position that I end up in is dependent on where I began and how much change has happened. How much I've been displaced from my initial place. And that is position. Now, do I want you to have those memorized? No, not really. I want you to understand where they come from. Okay, so have your calculator handy and let's look at example 5. So this says an object moving along a curve in the xy plane has position x of t, y of t, at time t, with dx dt equals t sine t, and dy dt equals cosine of t squared. At time t equals 2, the object is at position 1, 4. Okay, first question, find the acceleration of the object at time t equals 2. So if you try this, we know that acceleration at time t equals 2 is equal to the velocity, or the derivative of the velocity, at time t equals 2. And so if I am going to substitute this in, what I'm going to be doing is taking the derivative of the velocity. Let me rewrite the velocity up here. T sine t cosine t squared. I'm going to be taking the derivative of the velocity and then substituting in t equals 2. Now, since our calculators won't do each vector byte together as components, you need to break the components apart and do the dx dt in your calculator once and the dy dt in your calculator a separate time. And I would do this all from the home screen. Now, there's several ways you could go about doing this, and one of them is by plugging in your functions into y1 and y2, or just typing them in every time you go to do the math. Now, again, remember your calculator needs to be in radian mode. And when we do this, we get the velocity is 0.077, comma 3.027. And that would be, sorry, not the velocity, the acceleration of that object at time t equals 2. All right, let's find the speed of the object at time t equals 2. Well, remember, speed is a scalar. Speed is the magnitude of the velocity. And so the magnitude of the velocity, let's erase the t and let's put a 2 in its place because that's what we're actually calculating. The magnitude of the velocity is the square root of dx dt squared. So 2 sine 2 squared plus cosine 4 squared. And I'm going to type that in my calculator. Now, one thing I want to caution you on is when you're taking the AP test, you don't have to show all of your work, but you do need to show what you are substituting into your calculator. So if I make this notation, this is enough to say, hey, I know I'm taking the acceleration at 2, which is the derivative of the velocity at 2. And since I've already notated what the velocity vector is, now all I need to do is plug it into my calculator, but make sure you show those steps. Also, make sure you show what you're typing into your calculator. So if we're doing the magnitude of the velocity at 2, I'm just going to make this quick notation. And yes, it's a little bit more work, but then when I get the value, they know where it comes from. All right, let's find the displacement. Let's find the displacement of the object from t equals 2 to t equals 7. And we know that the displacement is the integral of the velocity vector from 2 to 7 dt, which means it's the integral from 2 to 7 of dx dt and the integral from 2 to 7 of dy dt, the integral of the components. And then I can type that in my calculator, and you can verify this with your calculator. I get the vector negative 6.362 and 0.097. All right, let's find the position of the object at time t equals 1. This is a start plus an accumulation. We know we're going to start at 2 because that's the only information I have. And I'm going to try to find the position at 1. So the notation would look like this. I want to find the position of the vector at 1. I know the position of the vector at 2. That was given to me. So if I take the integral from 2 to 1 of the velocity vector, I will get the position vector at 1. And so really what this looks like is we know this is the vector 1, 4. And if I do the integral from 2 to 1 of v of t, velocity vector, then I get the integral from 2 to 1 of t sine t and the integral from 2 to 1 of cosine of t squared. And so adding those together, we get negative 0.440 and 4.443. And that would be my position at time equals 1. So once you get the hang of what the position, velocity, and acceleration are, the math is the same as it has been for all of our position, velocity, and acceleration. We just have to understand that this is vectors. So I've got to take the derivative or antiderivative of each of those. All right, you guys, and you've done it. We've made it through. We'll talk to you later.